His live is training on or
Yeah, it is.
That is
I
on
see
and
the
we
icon.
take care of now.
Meeting is being live streamed.
okay. So we'll start now. All right. So this is the second talk of Professor Ravi Raghunathan from IIT Bombay. He is continuing on Harish-Chandra's finiteness theorem. Before I hand over to him, I'll just mention that this is the last lecture of the second trimester, and the third trimester is going to start from 30th April. And the first speaker there is Min Yong Kim from Edinburgh, and he will speak on a non-expert introduction to Lagrange functoriality. So I just wanted to remind everybody for that. And now I will hand over it to Professor Ravi Raghunathan. Yeah.
Okay, yeah, thank you, Shiv. So, yeah, I think I have slightly ambitious task today, but let's see. I think I should be able to finish. So I will first recap very briefly what happened yesterday. Actually, not so much a recap, but just, maybe a couple of definitions. Okay, so there's some. Okay. All right. So let me just remind you, right? So what an automorphic form is, it's a function on GA, complex valued, and it satisfies four properties. The first is left GF invariance. So phi gamma G is phi G. We've also assumed that the phi is K finite on the right, and ZG finite. Okay. So you can view phi as a function individually of just of G infinity, fixing GF. So G, you decompose the G as G infinity times GF, right? So this is the usual decomposition of the Adel group into the Archimedean part and the finite part. And then when you view your function phi as a function of G infinity, having fixed the GF, then you demand that it be ZG finite. And the fourth condition was that of moderate growth, which I spent some time explaining. And one of the things we did yesterday was to construct something called a Siegel domain. And we said that, look, instead of checking in some sense on the whole of GA mod GF or G1 A mod GF, it's enough to check your property on what is called a Siegel set or a standard Siegel set. Now, because phi is K finite, right? The right translates of phi basically span a finite dimensional vector space V0, and you look at the irreducible representations that occur in that space V0, and you call that set of irreducible representations, isomorphism classes of irreducible representations, you call that theta, and then that is called the K type of phi, okay? That finite set. And likewise, there's an ideal J of finite codimension that kills phi, and okay. So this data together, so every, corresponding to every automorphic form phi, we have this pair J, which is an ideal of finite codimension in the center of the universal enveloping algebra, ZG, and theta, which is a finite set of irreducible isomorphism classes of irreducible representations. And so I will denote by AJ theta the vector space of automorphic forms of type J theta. And the main theorem, the theorem that we want to prove in these two lectures, is the theorem of Harish-Chandra, which says that if you fix J and theta, the dimension of the space AJ theta is finite. Okay, so that's the main theorem. We also talked about cusp forms yesterday. So they are automorphic forms which satisfy an additional property. Okay. So I realize now that in this recap, I've forgotten to mention another property, which is how the center acts. So we will say that a function on automorphic form, for example, phi, right, satisfies the property A phi if the center ZA of the group GA acts by a unitary character, right? And then there is another condition which we call the cuspidal condition. So continuous function phi from GA to C is called cuspidal. If for every G in GA, integral phi ng dn, where you integrate over UA by UF, that integral should be 0. So what is the UA by UF? Right? The U is the unipotent radical of a proper parabolic subgroup, yeah, with Levy decomposition mu of G, and this statement, this cuspidality condition should hold for the unipotent radical of every proper parabolic subgroup. Okay. So an automorphic form satisfying A5 and A6. So A5 is not on the board, but that says essentially that the center acts by a unitary character. So an automorphic form satisfying A5 and A6 is called a cusp form. Yeah. And the space of cusp forms will be denoted A0 J theta, yeah, cusp forms of type J theta. And we had also done one more thing. We had kind of split off a part of the center of G, and we had written G as Z greater than 0 times G1. So G1 was the set of elements in GA with the property that absolute value of determinant G is 1. So you call G1, and what remains is something that I call Z greater than 0. It's a part of the center. And we saw that there was no loss of generality in assuming that the automorphic forms we consider are actually Z greater than 0 invariant. The advantage of, among other things, of passing through to G1 is that G1 modulo GF has finite measure. Or in other words, GA modulo Z0, Z greater than 0 times GF, that has finite measure. So the way we will prove this theorem, one, is we will actually prove the weaker theorem, which is that for a fixed pair J theta, the space of cusp forms A0 J theta has finite dimension. And so the first thing I'll do is reduce the proof of theorem 1 to the proof of theorem 5. Okay, so that's the argument I'm going to present now. Okay. So this was a recap. I don't want to say too much more about what I did yesterday. Hopefully, since it was just 24 hours ago, people remember what was said. And in any event, since I have only so much time, I'll stop with the recap there. But so right now, I'll focus on proving why theorem 5 implies theorem 1. Okay. So the first thing is, you take the so-called constant terms. So, if you have your parabolic and P equals mu, right? Usual Levy decomposition. And if you have an automorphic form of type J theta, right? For a fixed K and K, you define the function f sub u of mk. That will be the integral over UA by UF, f u mk du. Okay. So since you have fixed K, this and you have integrated out the U part, right? The Iwasawa decomposition will tell you that what you have is a function on automorphic form. What you have is a function on MA, and the proposition asserts that this is actually an automorphic form. So let's briefly see why this is true. It's not too hard. So if you look at this object, more or less by definition, right, it is obviously invariant under MF. I mean, it was invariant to start with under GF. So obviously it is going to be left invariant under MF. It is obviously going to be K intersection MA finite. Okay. That also you can see easily. And so if you look at the K intersection MA span of this function, you will once again get a finite set of irreducible representations, which I will call theta prime, right, of K intersection MA, and which occur in this K intersection MA span of this function. So that will be your type in this case. And of course, this theta prime will be completely determined by theta, right? Now, if Gothic M is the Lie algebra of capital M, right? There's a theorem of Harish-Chandra, if you like, that there is a non-zero homomorphism from the center of G to the center of M. And in fact, that Zm is a Zg module of finite type. So the upshot of all of this is that R of J is actually going to be an ideal of finite codimension in Zm. Right? So we've got all the ingredients in some sense to say that F sub u is an automorphic form. And M is going to be a product of groups of the form GLN. And therefore, you can assume inductively, right, that the dimension of ARJ theta prime, right? So this is the space of automorphic forms on MA of type RJ comma theta prime. You can assume inductively because what you will have in M are smaller. M is going to be a product of GL Ni, and the Ni's are going to be less than N. So inductively, you can assume that this dimension is finite. Okay. Now, suppose you look at the map mu, which takes f to the tuple f sub u alpha. Okay, where these u alphas, they basically vary over the unipotent radicals of parabolic, say p alpha. So there's an indexing set, let's call it Q, and this is an indexing set for the GF conjugacy classes of maximal proper F parabolic subgroups, right? And so what we have just seen is that the image of this map is necessarily finite dimensional, right? By induction. If I'm able to show that the kernel is also finite dimensional, then basically I'll be done, and that's the point. What is the kernel of this map, right? So it's easy to see that the cuspidal property for maximal proper F parabolic subgroups implies the cuspidal condition for all proper F parabolic subgroups. That's not hard. And therefore, the kernel of mu is exactly A0 J theta, right? So this shows you that in order to show that the finite dimensionality of AG theta, it's enough to show the finite dimensionality of A0 G theta. So again, just to repeat, the takeaways are, just take all the constant terms and look at the image. That image must be finite dimensional on the one hand by induction. And on the other hand, the kernel of this map is essentially the space of cusp forms of type J theta. Okay. Any questions so far? So this is the first reduction. So bottom line, to show the finite dimensionality of the space of all automorphic forms of type J theta, it is enough to show the space, a finite dimensionality of the space of cusp forms of type J theta. All right. So now the rest of the lecture will focus on proving theorem 5. Okay. Oh, okay. All right. So I'm wondering whether to prove this next lemma, but let me state it anyway. Right? So we'll need a couple of theorems from functional analysis, not very difficult. In fact, so let's do the following. So what I want to do now is I will want to say that, look, theorem 5 will actually follow if I know that cusp forms are bounded on Siegel sets, bounded functions on Siegel sets. And so let's see how we show that that's enough. Okay, so let's take a locally compact space X and mu a finite Borel measure on X. So of course, for us, the space X that we have in mind will be the space G1 by GF, or in other words, GA mod ZA GF. So F infinity will be the supremum norm on this space of functions. And there's a pleasant lemma of Godemo which says the following. It says that if you have a closed subspace of L2X, which has the property that the sup norm is bounded for every f in V. That is, if you have a closed subset of L2X which consists of bounded functions, then it is necessarily finite dimensional. Okay. All right. Okay. So maybe I will just give a proof of this since it's not hard. Right. Suppose you do have such a suppose you have V, a closed subspace in L infinity X min. Okay. I mean, suppose V is a closed subspace and it's also contained in L infinity X min. Right. That's what it means to say that every f in V is has finite sup norm. So for each f in V, you can look at the L2 norm, and of course you can bound it, right, using Cauchy-Schwarz by the measure of x to the half times the infinity norm. Oh, sorry, there's no Cauchy-Schwarz here. You just pull the f infinity out. Yeah. Okay. So yeah, sorry, I misspoke. Here you just pull f infinity out. Okay. So what that says is that if Fn goes to f in sup norm, right, necessarily it goes to f in L2 norm. So V is automatically closed in L infinity x. Right. Okay. So being closed in L2 is automatically going to ensure it's closed in L infinity. So it follows that the identity map, right, from V to V, viewed as the first V is viewed as a subspace of L infinity x mu, and the second V is viewed as a subspace of L2 x mu. This is a bounded operator from a continuous operator from a closed subspace to a of L infinity to a closed subspace of L2. Right? Okay. So when you have a continuous map of two, say, Banach spaces, then of course you can use the open mapping theorem to say that the inverse is also bounded, right? So there exists a capital M greater than 0 such that norm F infinity is less than or equal to M times norm F2. So inverse being continuous guarantees this. But what this means is if I take an orthonormal set of functions in V, right? And with respect to the L2 norm, then for almost all x, you can look at the absolute value of any linear combination, summation Ci Eix, right? That can be bound, that is of course bounded by the infinity norm, yeah, by definition. And that in turn is less than or equal to this bound M times the 2 norm, right? Okay. Since these are orthonormal functions, right, the 2 norm is simply given by, in this case, will simply be given by summation Ci square. Now, you take Ci to be Ei x bar, right? So when you do that, this will simply become summation absolute value of Ei x square. That will be in turn less than or equal to M times the summation of the absolute value of Ei x square to the half, right? That's the what we had just before, the previous inequality. So basically the M, you have summation absolute value of Eix square is less than or equal to M square. And what then happens is essentially that N is less than or equal to M square times mu of X. That's what you end up getting because remember you already had this particular thing where you had norm F2 is less than mu X to the half times F infinity. Okay. So bottom line is that N, the possible, there's a bound on the number of, on the cardinality of the orthonormal set of functions in V. In particular, therefore, the dimension must be finite dimensional. Okay. So this proof, by the way, is due to Herman. All right. So let's move on to L2 cusp forms. Suppose phi. So previously we defined a cusp form only when phi was continuous, right? So if you have just some function, not necessarily continuous, which is invariant under z greater than 0, right? So you have a function which is left invariant under GF and also under z greater than 0. And suppose it is square integrable on GA mod z greater than 0 GF, then we will say phi is cuspidal if for every smooth function with compact support in GA, phi convolution f is cuspidal, right? So phi convolution f will be a continuous function anyway, right? Because you have a convolution of a L2 function and a C infinity function. So phi convolution f being cuspidal has already been defined. Okay, so now this is the definition for a general function. And the subspace of such functions, cuspidal functions in L2, z greater than 0 GF, GA modulo z greater than 0 GF, that I will denote by L2 cusp. Okay. And it's relatively easy to prove the following statement. Right. So the statement is that L2 cusp is closed in L2. Right. It's not particularly difficult. It's a more or less simple exercise in, I don't know, LP spaces or whatever. So I will not prove this, but what I will point out is that in order to show that A naught J theta is a closed subspace of L2, it is enough to show that A naught J theta is a closed subspace of L2 cusp. This is the point. So why am I doing all of this? The point is, we had Godmon's lemma. So let me just remind you. Godmon's lemma says that if I have a closed subspace of L2x, which has the property that it consists of bounded functions, then it's finite dimensional. So what we first need to show is that the space that we are interested in is, of course, A naught J theta. And we would like to say that A naught J theta is, first of all, a closed subspace. So all of this, these arguments are in that direction, right? So if I have, so first what I do is I identify a closed subspace of L2 and call it L2 cusp, and I show that A naught J theta is a closed subspace of L2 cusp. Okay. So let's prove proposition 4. Okay. So basically, you have to say that, if you have a sequence phi n going to phi, then that remains in a naught j theta. Okay. All right. So suppose phi n goes to phi in L2 with phi n in a naught j theta, right? Then what can I say? Okay. So first of all, remember that the measure space we are looking at is finite, right? It is G1 by Gf, and therefore L2 convergence implies L1 convergence by Cauchy-Schwarz, right? And in particular, therefore, you have convergence in the sense of distributions. Okay. So I'm giving the proposition, proof of this proposition because there are, some ideas which are often recurrent in this game. So what you have initially a priori is convergence in the sense of distributions. So in particular, that means that if I take any x in the center, x is after all some kind of differential operator, right? Then xfn will automatically go to xf in L2, right? That's part of the machinery of convergence in the sense of distributions, that they will then converge even when you apply differential operators. So it's also easy to see that if phi n is of a certain type, so pi, right, that is for some pi in k hat, then so is phi. At least almost everywhere, that's not hard to check, right? So phi n transforms in a certain way under k means that the limit will also do that. The simple write down integral and check it. Okay. So phi is k finite is easy, and it's also zg finite as a distribution because each of the fn's were zg finite. But if you know this, then these operators in zg, they are basically the relevant operators are elliptic operators, and there's a theorem called the regularity. I mean, there's a theorem which goes by the name for regularity theorem for elliptic operators, and that shows that in any such situation, phi must be analytic. So basically, you're saying that you see, being zg finite means phi satisfies a suitable partial differential equation, which happens to be have an elliptic partial differential operator. And in that case, because you have k finiteness also, that's crucial, right? You can show that the phi itself must be analytic. So this means that phi is indeed in a naught j theta, and that a naught j theta is closed in L2 cusp. Okay, so this proves what we want. So again, just to remind you now of the structure of the proof, you want to prove theorem 1, which says that the space of automorphic forms of a given type j theta is finite dimensional. We have reduced it to showing that a naught j theta is finite dimensional, right, by using the constant term arguments. Then to show that a naught j theta is finite dimensional, I want to say that using Goldman's lemma, it is enough to show that a naught j theta is a closed subspace of L2, and that it consists, the second part of Goldman's lemma will say that you need to show that it consists of L infinity functions, bounded, in other words, essentially bounded functions. And that is what we will do next. So this is what we really need to prove, right? Proposition 5. If phi is a cusp form invariant under z greater than 0, then phi is bounded. So this is what we finally need to prove, and this is what we will spend the rest of the lecture proving. So phi is bounded, and hence square integrable is obvious. We are on a finite measure space, so bounded functions are of course in L2. Okay. In order to prove that phi is bounded, it is of course enough by left invariance, left GF invariance, to show that it is bounded on a standard Siegel set. Okay, satisfying theorem 4. Theorem 4 was from yesterday. So that was a theorem of Minkowski, which said that there are always Siegel sets S such that GF times S is all of GA, right? So S kind of functions like a fundamental domain for the action of GF on GA. And what yesterday's lecture said that reduced checking various properties like rapid decay, etc. So if you want to check rapid decay of a form, what we said yesterday is that it's enough to check it on some Siegel set, and we wrote down what it meant to have rapid decay on a Siegel set. So that was in terms of some, okay, so we'll see that anyway, again. Right? In fact, we will prove that phi has rapid decay on a such a set, not just bounded. And by the way, in these slides, especially in this proof, we will follow the exposition of Goldfeld and Jacquet almost verbatim. So I had made a reference to these notes yesterday, and you will find the link in yesterday's lecture notes, lecture sites. Okay. So basically now I'm going to prove proposition 5. So even if, you haven't followed things or how this reduction came about, in some sense, we are starting from scratch here, and it's enough to, you can start to follow this argument again. Okay. So yesterday we already saw that, if I have an automorphic form, then there will be, we can always find an f in CC infinity of G1 such that f convolution phi is equal to phi. This was a lemma of Harish-Chandra or so that's our starting point. So we'll choose such an f, right? So the Iwasawa decomposition for G1, right? So we all saw that yesterday. So G is NAK, but G1 was decomposed in some way as N and K are anyway in G1, but A, you have to take a little care. So it was decomposed into A sub 1 and A superscript 1, but never mind. What it says is that if you look at phi of A omega, okay, so remember we had written G as A times omega. So part of the machinery of Siegel sets was, if you're looking at phi of G, it's enough to look at phi of A omega, where A lies in a certain set AT and omega lies in a compact set. So this A is in that set AT, which was described yesterday, right, in terms of some condition on the roots of GLN. Okay, so the alpha I of A were less than or equal to or greater or equal to T. And that's how you got the A's. So we have the Iwasawa decomposition, and I've just written it out. So it's integral over N over A and over K, phi of U B K, f of that, sorry, that should be f of omega inverse, not f of omega minus 1. That's an inverse. So I've just written down the definition of convolution of f convolution phi on the right hand side, and this is what the Iwasawa decomposition tells us. Delta B is, of course, a modular character of A. So everything is, there are a number of typos here. So U is an N, which is this math N is nothing but the adelic points of N, unipolar group. B will be in A, and A itself is my notation for take the adelic points of the diagonal group A and intersect it with G1. And K will, of course, be in the usual compact set. So because F has compact support, it is easy to see that the elements A inverse B remain in a compact set, omega A of A, when you're looking at this integral. Okay. So that's not hard to, and you can verify that. Now, using the left NF invariance of phi, right, you can rewrite this integral. So first, all I did was I wrote phi as F convolution phi, right, kind of smoothed it out by convolution. And then, although it just remains phi, is the point, right? Then I use the Iwasawa decomposition to get an expression for phi of A omega. And then I'm using the left NF invariance of phi. And so then the integral above becomes integral over K integral over A, N by NF. And then I will sum over gamma and NF. And the sum of the function F W inverse, A inverse, gamma U B K, right? So I've just written, replace U by U times gamma on the one hand. And on the other hand, I'm integrating over N by NF. Okay, so this is NA by NF basically in my notation. Phi UBK du delta B inverse dB dk. Okay, so this is a kind of unfolding. We have written the integral over N as an integral over N by NF, and then a sum over a gamma in NF. Okay. So we'll come back to this expression shortly. We will need to. But I'll just remind you that if you have a subset theta of the positive roots delta, then you can associate a parabolic, let's say P theta with Levy decomposition M theta V theta, right? And we let N theta equals M theta intersection N. And then N is nothing but N theta V theta as a semi-direct product where V theta is normal in N. Okay, so I don't want to get too much into this, but here is the point. If you're not familiar with this kind of stuff, for example, if you take the simplest case GL2, there is only one root, essentially alpha, so the positive root. So the only subsets that are possible are the theta may be the empty set or theta may be consists of this one root alpha. And then there are two cases. If theta is the empty set, then you just get the group GL2. So this P theta is in fact not a proper parabolic, it's just the full group P. And in that case, M is just all of G and N is the other way around. Right. Yeah. And then I have, unipotent radical is just the V theta becomes all of N. And in the other way, if I take theta equals alpha, then I just get the Borel subgroup. Okay. All right. So this is what's going on here. And what you're saying is you can write the full unipotent radical as N theta times V theta as a semi-direct product, right? So V theta is the unipotent radical of your proper parabolic, say. I mean, not necessarily, but okay, if a proper parabolic, then you can write your unipotent radical N as N theta times V theta. So N theta is the part that is not contained in the unipotent radical of the parabolic. Okay. So the idea, we had this integral and then we had a sum inside. The idea is to replace this sum by a more tractable alternating sum. We will do that now. Okay. And this sum will be over the subsets theta of delta. Okay, so let's look at this alternating sum. You sum over all subsets of the positive roots, right? Summation -1 to the absolute value. So this cardinality of theta. So this absolute value of theta thing is actually cardinality of theta, right? And then look at the integral V theta gamma in N theta F, right? F omega inverse A inverse gamma V U B K dV. Okay, so instead of, so I'll just remind you, right? So the previous sum looked like this, gamma in NF, but instead now we have gamma in N theta F and we have integrated over V theta. Okay, V theta is nothing but the idyllic points of Roman V theta. Now the point is, right, if theta equals phi, then what you get exactly this sum back, right? Look at the term corresponding to theta equals empty set. Sorry, I shouldn't call it phi, empty set. So if theta is the empty set, then what you get is exactly gamma NF F omega inverse A inverse gamma U B K, right? So this was what there was. This was the term that we started with. That was inside the integral. Okay. On the other hand, if theta is non-empty, we will analyze the sum again. Okay, so what happens there? Let's see. So what we want to say, of course, is all the other terms are 0. So then we can replace the sum that we started with by this alternating sum. Okay. So suppose theta is not non-empty, then what happens to the corresponding integral? First of all, the corresponding integral in the alternating sum is invariant again under V theta and N theta F. So let's look at this, right? So you're integrating against V theta. So of course it's invariant under V theta and you're summing over N theta F. So of course it's invariant under N theta F on the left, right? So therefore it's also invariant under NF because N is nothing but N theta times V theta and it's invariant under both of those things. So if I integrate over N by NF, then what do I get? The term that looks like integral N by NF, integral over V theta, and then you have this gamma and N theta F, and you do the summation. Okay. But now you can decompose this integration over N by NF as an integration over N theta by N theta F and V theta by V theta F. And you can do this because V theta is a normal subgroup of N theta. Okay. So I've been a little careless about my notation. U is of course in N, but over here I've not bothered to write U again as a product N theta V theta. I've just retained the variable U. So the point is, I started with some sum. I've replaced it by an alternating sum, and I'm looking at each of the terms in the alternating sum. and each term in the alternating sum corresponds to a subset theta of the positive roots, in other words, a parabolic subgroup of G. And I'm looking at sums over gamma in the unipotent radical n theta of that parabolic subgroup, n theta f, and I'm integrating over v theta. Yeah. And when you do this, right, since v theta is, of course, the unipotent radical of a parabolic subgroup, right, the cuspidal condition says that integrating over v theta by v theta f, integrating phi on that thing will give me 0. Okay. So this term ends up being 0. So the inner integral is 0. So what is left is only so for every time theta is non-empty, all the terms in the alternating sum basically give us 0 when you integrate. Okay. So that means that the original term can be replaced by this alternating sum. Okay. And so what we are writing is phi of a omega is nothing but integral n by nf times integral a1, integral over a1 times integral over k of some s, that's my name for the alternating sum, delta inverse b, phi u b k, du, dp, dk. Okay, so the entire argument here was you had some sum, you replace it by an alternating sum. The terms in the alternating sum that correspond to non-empty subsets of the positive roots all give me 0 because of the cuspidality condition, cuspidal condition on phi. Okay. All right. So as I said, there's a phi u b k here, but okay. So I should have really decomposed that, but anyway. All right. So what we have is this finally, right? Phi a omega. This is what I had written in the last line of the last slide. And S is this thing. Sum theta subset of delta minus 1 to the cardinality of theta, integral v theta dv, and the sum gamma and n theta f omega inverse a inverse gamma v u b k. All right. So that's where the thing is. Okay. So now we would like to attack this sum and get our estimates, show that phi a omega is rapidly decreasing. Okay, how to do this? Okay, we may analyze the sum by passing to, okay, so I'm going to call the adelic points of the Lie algebra of n, I'm just going to denote it by this Gothic n, okay? I'm not going to write NA each time, I'm just going to write n. And I'm going to follow this notational convention for all the other Lie algebras, right? For the rest of this lecture. So for example, when I write n equals v theta plus n theta, I mean this, I'm looking at the adelic points. Similarly, so what you do have, right, because you know that n is equal to v theta times n theta as groups, semi-direct product, the Lie algebras break up as direct sums. N equals v theta plus n theta, all Gothic. Transpose Gothic n equals transpose Gothic v theta plus transpose Gothic n theta. So in the Lie algebra level, you have these two Lie algebras and statements about their adelic points. Then this alternating sum, right, I'm now going to write it in terms of the, so this integral was an integral over over n theta, right? But what sorry. So I have my variable, where is it? My variable is v, right? So I have this expression here, and I will replace it because I have an isomorphism between x and, I mean, the map x goes to I plus x gives an isomorphism between the nilpotent Lie algebra and the group, right? I can simply replace my previous integral over v theta by an integral on the adelic points of the Lie algebra v theta. That's all I'm doing. So I've simply replaced my variables. So I've taken my gamma and I've replaced it by 1 plus psi, right? And I've taken my v and I've replaced it by I plus x. Okay. Now this, so I already said last time that, most of our arguments anyway work in general, for general reductive G such that GC is connected. But the main reason to, at some point, go to GLN was because notation becomes simpler. And here is one place, because here I can just take x goes to I plus x, but in general, I would have had to use the exponential math. Not a big deal, but I wanted to avoid that. That's all. So, okay. So now let's change variables here in this expression. Okay. So x goes to 1 I plus psi inverse times x, you substitute. So when you do that, it is not hard to see, right? So you replace x by I plus psi inverse multiplied by x. So then when you multiply I plus psi by that, you will get x back, etc. So when you do the change of variables, your alternating sum becomes a sum over integrals over v theta of f omega inverse a inverse 1 plus psi plus x u bk dx. Okay, I mean, this obviously is something you have to work out. Now, this sum above, I'm going to use the Poisson summation formula to analyze it, right? So, and for this, the Poisson summation formula for n. So, basically, n is the adelic points of Na, so Na by Nf kind of thing. So, if I have x in n and y in transpose of n, then we have a duality given by the pairing x comma y equals trace xy. And incidentally, I can restrict this pairing, of course, to n theta, and I will then get a pairing between n theta and transpose n theta. Right. Okay. So if I have a non-trivial additive character, right, from A to C, I can, on the adels, I can define a Fourier transform of a function f on n theta as f hat y, usual thing one does, f hat y will be integral over n theta, f of z, psi of trace zy dz, and this will be a function on transpose of n. So, sorry, it should just be, in my notation, it should just be transpose n. Okay. I mean, it is the adelic points, but it should just be transpose n, because that's my convention. Okay. So the point is, Poisson summation formula is valid in great generality, right? If you remember, the formula for a lattice Z, the lattice Z sitting inside R is just saying that summation f of n is equal to n summed over Z is summation f hat n summed over Z, provided the function f is nice enough. Okay. So, for instance, here my f is, has C infinity with compact support. So certainly it's nice enough. So we can apply the Poisson summation formula to this function. So for the function capital F, here is the function you take. You take f of z. It's the function that appears in the integral above, right? So you take f of z equals integral over v theta of f of omega inverse a inverse 1 plus z plus x times u bk dx. So that's my function. And you apply the Poisson summation formula for this function, right? Because this is a sum over n theta f, right? So you apply the Poisson summation formula, what will you get, right? So summation f, capital F of, roughly speaking, right? Summation capital F over lattice points is equal to summation f hat over dual lattice. That's what the Poisson summation formula says. So here is a dual lattice. I have lambda in transpose n theta of f, right? The f points of transpose n theta. Integral over n theta, integral over v theta. Integral over n theta comes from the Fourier transform. So integral over v theta, f of omega inverse a inverse 1 plus z plus x u bk dx psi of trace z lambda dx. So I've just applied the Poisson summation formula, and this is what I get. I've converted a sum over n theta f to a sum over the dual lattice. Okay. Let's see where one goes with that. So if I look at this sum, it's some complicated thing, doesn't matter. But notice that I can do one thing. You see, I have both n theta and v theta here. So I can basically collapse them into, remember, n theta times plus v theta is basically capital N, right? The whole, the Lie algebra of the whole of the unipotent group. So, of G. So if you take the sum, it can be rewritten as summation minus 1 to the mod theta, cardinality of theta, summation lambda in transpose n theta f, this as before, but now I can replace the two integrals over n theta and v theta by a single integral over n, f omega inverse a inverse 1 plus x u bk psi trace x lambda dx. So this x now varies over n. So this, you kind of collapse two integrals into one. And so now it's a matter of estimating this sum. This is what one wants to do. Okay. So if you do it, right? So finally, S, this was all an expression for S, that alternating sum. So what we have is S is summation over subsets theta and delta minus 1 to the cardinality of theta. And now I sum. So previously I had lambda in transpose n theta f, but I will replace it by summation of lambda and transpose n f. Not all lambda, of course. I'll put a prime there to indicate that some lambdas are missing. So which are the lambdas missing? The sum here, the second sum, is only over those lambda not belonging to some transpose n theta f for some theta not equal to 5, right? So that's exactly what it is. The original lambda was in a transpose. Sorry, so yeah. So it should be belonging to, I guess, some transpose n theta f for theta not equal to 5. So there's a typo there. So in any event, there is a sum here over transpose n theta f, but I'm changing it to a sum over lambda and transpose nf. Okay. So once again, you can rewrite that sum, right? The sum over some lambda in transpose nf, some prime, right? Integral over n. So all I've done here now is rewrite what's inside the f. So, f was omega inverse A inverse, but now I'm replacing 1 plus x by A inverse x A inverse, and I'm putting an A inverse on the right. I'm putting a U A inverse BK. So I'm basically introducing an A inverse into the thing, and then introducing an A again to make sure that I've not done anything wrong. So there's a reason for this change. One wants to basically go from x to A inverse x A. So if you change variables, so first of all, you have trace. So you change variables and you send x to A, and you use the fact that trace of A x A inverse lambda is nothing but trace of x times A inverse lambda A, right? So you just take this A here at the start and put it at the end, because trace of AB is trace BA. So what we see is delta B inverse times S, that's the alternating something, right? That is delta AB inverse, sum prime. And then I've just changed the variables and use the fact that I mentioned above. Okay, so I have f of omega inverse 1 plus A inverse XA, A inverse U, A inverse BK, psi trace X, A inverse lambda A. So I'll try to tell you what. Okay, so why have I written it like this? Because you already know that if you look at the elements omega, that varies over a compact set, A inverse UA and A inverse B and K. All of these things that appear in the expression, they vary in compact sets. So if I look at the functions x going to delta AB inverse times f omega inverse 1 plus A inverse XA, A inverse U, A inverse BK, we look at this bunch of functions, right? These functions remain in a compact set in the space of Schwarz-Brouwer functions on G1. Right? So because all of these elements, omega, A inverse, etc., remain there. If you're just taking your function and translating it by these elements, right? Those translates will all remain in some compact set. And now I will state a lemma, which I will not prove, but it is actually quite elementary. Okay, so maybe after stating it, I will say roughly what's going on. Suppose B is a compact set in the space of Schwarz-Brouwer functions on transpose N. Then for any M1 greater than or equal to 1, there exists C1 greater than 0, such that for all phi in B, right, in this compact set, and A in AT, so the absolute value summation lambda and transpose NF phi prime, right? The usual summation with certain lambdas excluded. Phi A inverse lambda A, you look at that expression, that is less than C1 times beta A to the minus M1. Remember, beta A was the product of the simple roots, alpha A. Okay. And this is exactly, to have a bound like this is exactly what it means for a function to be of rapid decay on a Siegel set, and therefore of rapid decay on G1. So the right-hand side is exactly what we need to say that a function has that kind of expression is what we need for rapid decay. And we are saying that if functions remain in some compact set, then we have essentially rapid decay for this sum. So this is all very complicated, but you could just think of the one-dimensional situation where lambda, say, is z, and you take f equals q, etc. So what we are saying is, if you take some function, let's say on the real line, like e to the minus x square, right? And I look at, say, something like summation e to the minus a n square as, let's say, so e to the minus a square, a n square, right? As n varies in z, then that has rapid decay as a function of a. This is quite elementary to prove. So of course, stated like this, one has to do a little more work, but nothing is really involved in this lemma. It can be done entirely by hand. So I will not prove it. But what we have just seen from this lemma is that all these things, the alternating sum indeed has exactly the right kind of decay property. So I will just do that on the next slide. So the lemma shows that delta B inverse S has this kind of decay property, is less than or equal to C1 times beta A to the minus M1. Sorry, that should be for any M1, not any M. So all of these U, B inverse, K, etc., all lie in compact sets. U, B, K lies in A omega for some compact set omega. That's our setup. And therefore, absolute value of phi of U, B, K, right, which lies in A omega, can be bounded by some C naught times norm A to the M0. Right? Remember, phi is just some continuous function. Everything is happening on some compact set. And the phi is anyway an automorphic form, remember. And therefore, is certainly bounded by C naught times norm A to the M0 for some M0. It has moderate growth for sure. But we're saying we can do much better. But now, this is phi UBK, but we already had, the other stuff, delta B inverse S, that was less than C1 times beta A to the minus M1 for any M1. So if I choose, so this is what phi omega is, right? So on the one hand, we have an estimate for this S inside, and we also have an estimate for phi UBK inside. Or rather, we have an estimate for delta inverse times S, and we have an estimate for phi UBK. Put that together, phi UBK is bounded by some norm A to the M0, but that's some fixed M0. So if I choose M1 large enough, right, then I have a minus M1 here. And what that says is, there is some constant K such that absolute value of phi A omega is less than or equal to K times beta A to the minus M. This is exactly what you need. This is the condition of rapid decay. And so this proves proposition 5. Okay. So all of this is to say that cusp forms have rapid decay. On the other hand, therefore they are bounded. Therefore, the space of cusp forms of type J theta is a closed subspace of L2 consisting of a finite L2 of a finite measure space consisting of bounded functions, essentially bounded functions, but in fact bounded functions. And therefore, by Goldman's lemma, the dimension of the space of cusp forms of type J theta is finite. Okay. So this proves what we want. So I will just conclude with a small extra point. So theorem 2. So if f is in smooth function with compact support and phi is in L2 cusp, then the convolution of phi with f, which I denote by rho f of phi, is a rapidly decreasing function on G1 by Gf. So the same set of arguments that I gave essentially prove this. So by our previous arguments, if you look at rho f phi, this is exactly what we computed, right? We had computed phi convolution f acting on A omega. So we had computed that to be this integral, n by nf, integral over A1, integral over k, s delta inverse b, phi ubk, du, db, dk. This is the expression we had. And we had already shown that delta b inverse in absolute value is less than C1 times beta A to the minus M1. So you just go through and do the estimates. So if you do that, you see that absolute value of rho f phi on A omega is less than or equal to C1 times beta A to the minus M1. This is the bound for delta inverse B S. And then you have this remaining integral over n, A1 and K, but that you simply bound by the L2 norm, right? So that's just less than or equal to C1 beta A to the minus M1, integral G1 by Gf, absolute value phi G dg. and that can be bounded by Cauchy-Schwarz by the square root of the measure of G1 by Gf and the L2 norm of phi. Okay, so that's it. L2 norm of phi is something fixed, and so the whole thing has rapid decay. Okay, so what is the, why is this useful? Well, this proves theorem, okay, 2. So here is theorem 3 now. Okay, I should say the numbering is slightly off. I will change it when I upload it, right? The numbering does not correspond to yesterday's numbering now. This theorem 2 and 3, I think. So I will change that number. It's only, anyway, the last slide. So if I have a sigma compact finite Borel measure space, which is what, of course, G1 by Gf is, right? With a countable dense subset. Suppose CBX is a space of bounded continuous functions with a sup norm. Suppose I have an operator T from L to X to CB, right? A continuous operator. Then T viewed as an operator on L to X is compact. So this is our situation, right? So we have just taken convolution with phi, and we produced, in fact, not just bounded functions, but rapidly decreasing functions, right? So what this is saying is, this such an operator is necessarily, if it's continuous, it's necessarily compact. So if you combine, so okay, this is exactly, so this should not be theorems 2 and 3, this should be theorems 6 and 7. I have typos there, right? So if you combine the previous theorem, which is what I'm calling theorem 6, although I've written 2, and this theorem, which is theorem 7, then that means that rho f is a compact operator on L2 cusp. And from that, you can easily check that L2 cusp decomposes as a discrete sum of unitary irreducible representations of GA. And each irreducible representation occurs with finite multiplicity, essentially a consequence of the spectral theorem for compact operators. So this theorem is a foundational theorem due to Gelfand and Piatetsky-Shapiro. It says that L2 cusp decomposes as a discrete sum of unitary irreducible representations of GA. And each irreducible representation occurs with finite multiplicity. In fact, for GLN, this multiplicity is 1, and this is called a multiplicity 1 theorem. And due to Piatetsky-Shapiro and Shalaika, this is also an important theorem. These are both foundational theorems together with the finiteness theorem of Harish-Chandra. And finally, the irreducible representations, unitary representations that occur in that decomposition, or rather their underlying smooth representations, are what are called cuspidal automorphic representations. Okay, so I will stop there. Yeah, thank you.
All right. Let's thank first, and then we'll come back for the question.
Yeah, yes, let's thank. Yeah, it was a very nice talk. And only, can you say something more about the importance of this finiteness theorem of finite dimensionality theorem of Harish-Chandra? That is where it is used later on, like that. Some more comments on the use or importance of this theorem. If you can comment.
In some sense, all over. No, I mean, so maybe I made some remarks yesterday, right? So, for instance, if you're familiar with modular forms,
yeah, that I understand.
The statement that modular forms of level n and weight k is finite dimensional. This is the
that's right.
theorem.
That's right.
So,
So that I got the point.
Yeah.
That this is the kind of a version or the more generalization of that one. So that is very nice for point actually that you have mentioned.
Yeah. So, I mean, it's used everywhere.
Use means
I'm not sure what more I can say.
What more can be said about it?
Because you usually want to know that various spaces are finite dimensional for various.
Yeah, right. That's of course.
So, of course, it's useful to know that.
Structure is, I mean, get some hold of the structure or knowledge about the structure is very important, of course. So that way,
I mean, in some sense, this is the basic theorem. I mean, this is the least you can say. Right?
Right. So,
I mean, this is a starting point.
Used in other theorems, later theorems of Harish-Chandra, like that.
Okay. I don't know about later theorems of Harish-Chandra, etc. I mean, I don't know. I'm not sure I can give a good answer to your question. I don't. Maybe Sandeep can say something. I notice he's there. If he's
there is a good article by Amin Sofi on finite dimensional subspaces. So he enumerates all kinds of conditions which forces space to be finite dimensional.
That is fine. Of course, here also there were some conditions mentioned. So that is fine. But anyway, it was very nice talk. Thank you for these two talks. Very nice represented. Yes.
Welcome.
Okay.
Thank you.
Yes. Yes, and also thanks to the organizers. Other Devendra Tiwari is here. I think he was here just now. Oh, yeah, he is here. Yes.
He's
Yes.
there.
So this is, and also thanks to the chair, Shiv Prakash Patel.
Oh,
Thanks to him also. Yeah. And I think one more talk is there in this second trimester. So Devendra has handled all these things very nicely. So I thank Devendra.
No more talks is remaining now.
No, not that.
was the last.
30th April is, that is the next one. That is the next one. No, that is for the third. Is it that is for the third?
30th April would be counted in the third trimester.
Third one. It is in the third one. Okay. All right. So anyway, Devendra has mentioned that he may not be available, but still I hope you are helping the organizers. And now we have requested Jewel to actually take over from you, and he will contact you and get your help in certain things about organizing other lectures and like that. So we have Jewel is at present a postdoctoral fellow at the Bhaskaracharya Pratishthan, and he will be actually carrying over your job so that you will be somewhat relieved of that. But still, I hope you are helping in the activity. Yes. Okay. Yes. Thank you. Thank you all. Yes.
Yeah, thank you. And thanks to the audience.
Yeah. Thank you. So let's. So are there any more comments and questions? Maybe not. Okay. Let's thank Ravi for the talk, his talk. Yeah. Thank you.
Thanks. We'll leave.
Okay, thanks, Shiv. So, and okay, so I will leave now. That's okay.
Yeah, I
I
think
hope
so.
to see you sometime. Okay.
Yeah. See you sometime. Yeah.
Bye.
Bye.